This is the Unit 3 Part 4 video series dealing with intermolecular forces. This is a review video on electronegativity, and this is the first review video that will help you study intermolecular forces. So by the end of this video, you should be able to define electronegativity, much like we were able to do when we did periodic trends. And also, you should be able to predict qualitatively the electronegativity of atoms based on where they are in the periodic table. Now, when I say qualitatively, I just mean be able to compare which one would have greater or smaller electronegativity. Things that you should kind of already be able to do. Okay, so let's talk about what electronegativity is. Let's work on the definition. The definition is pretty straightforward. It's the way that atoms want to attract electrons, or it's how much atoms want to attract electrons when they are in a bond. So we have a couple of different samples here. Okay, so now what we have is a bond with two chlorine atoms. Okay, there's a single bond in between here, and let's keep in mind that a bond, this line, is actually representative of two electrons. So what I'm going to do is keep in mind that those electrons are moving. They're in constant motion. They're moving all around. Okay, they're not stationary. And so yeah, they move in between the two atoms, but they also move around the atoms too. They can go like this, okay? And so they're moving, they're bouncing in between, they do this. Now, the idea here is because these two atoms are the same, they really aren't attracting the electrons in that bond any differently. But now if we go down below here to this atom, or this bond, again, the line represents two electrons, okay? Let's look, and I'll do this one in a different color here. Hydrogen has a different electronegativity than chlorine. So yeah, the electrons are still moving, bouncing back and forth in between, but they're also moving around hydrogen and they're moving around chlorine. But which one is more electronegative? Chlorine is more electronegative. So that means that the electrons are found a little bit around hydrogen, but they're found really circling a ton around the chlorine. And so that's what electronegativity is. It's the unequal sharing, really, of the electrons. And the one with the greater electronegativity is the one that really wants the electrons. So chlorine has the electrons found around it way more often than hydrogen. And so in this case, what we do is we can symbolize that unequal sharing. If chlorine has the electron more often, that means it's going to have extra negative charge. So that extra negative charge is symbolized with a lowercase Greek letter delta and a minus. So this side here has a partial negative charge. That partial negative charge is because that atom has more electronegativity. So just like this is partial negative, that means that this side with the hydrogen is partial positive. And again, keep in mind the partial means that it is, I'm sorry, not that partial isn't meaning anything. You can get your facts straight, Walsh. That partial symbol is a lowercase Greek letter delta, and when I write it almost like I would write an 8, and I don't connect the 8 finally, okay? And then there would be either a negative or a positive there, depending on if it's partial positive or partial negative. Okay, but let's talk about this qualitatively. Let me pull this down so that you can see it a little bit better. Probably good. Okay, and so keep in mind, just like we had said in the periodic trends unit, that fluorine is the most electronegative element, and the further you get from chlorine, not by column or by row, but just by number of atoms, the further you get away from fluorine, the less electronegative the atom is. So francium, which is found here, is actually the least electronegative element. And so you can see this trend on the periodic table. Fluorine has an electronegativity of 4.0. Francium has an electronegativity of somewhere around 0.7, like cesium. So the electronegativity is really varies as we move across the periodic table. And so this is a three-dimensional thing. You can see this is the biggest, and then these two are the next biggest. Oxygen, if you need to know the second most electronegative element, that's going to be oxygen. Nitrogen, sulfur, bromine, they're all kind of the same, and then carbon, and so on and so forth diagonally as we go across the periodic table. Now, why don't these have a reported electronegativity? Well, it turns out that the noble gases do not form bonds. They don't bond with anything. And so because they don't bond with anything, or they don't want to bond with anything, they have zero electronegativity. Now we know that xenon and krypton, we've seen some examples where those two bond, but in general, all the noble gases do not have an electronegativity, because in order for it to have an electronegativity, it needs to share electrons with something, and those atoms typically do not. So, okay, so let's try it yourself. Oh, I better move this down so that you can see it too. Holy cow. Okay, try it yourself. Okay, so if you need to, you can pause it. I probably should have. But if you need to, pause the video. And when you pause the video, see which one has the greater electronegativity of the pairs. Okay, so I assume you pause the video. So now it's just a matter of us trying to figure out which one is the closest to fluorine. The greatest electronegativity, again, is fluorine. So the closer you are to fluorine, by placement on the table, is going to be the one that is the greatest electronegativity. So the first one is actually fairly simple. Fluorine is the most electronegative element, so therefore it must have the greater electronegativity. Now, when we compare rubidium and lithium here, remember the electronegativity increases as we move up, so that means that lithium is the greater electronegativity of those two. And then when we compare niobium to molybdenum, keep in mind that as we go across the periodic table, the electronegativity goes up. As we get closer to fluorine, the electronegativity increases. So the greater electronegativity in this case is molybdenum. So that concludes your review video. Hopefully this will help you in determining how electronegativity plays a role in intermolecular forces.